July 14th, 1944. A Sherman tank lurched forward across a French field near Isigny, a town barely 8 miles inland from Omaha Beach. Lieutenant General Omar Bradley stood watching, arms crossed, as the tank's commander revved the engine. The target, a hedgerow, sat 30 yards ahead, ancient dirt embankment, 4 feet high, crowned with centuries of tangled blackthorn and oak roots. The kind of obstacle that had turned the Normandy breakout into a grinding meat factory for 6 weeks. The tank accelerated. 10 miles per hour, then 15. What happened next shouldn't have worked. The Sherman didn't ride up and over the hedge like every other tank Bradley had watched try this maneuver. It didn't belly up, exposing its thin underside armor to German gunners. Instead, 4 steel prongs welded to the front of the tank bored into the earthen wall like tusks, pinning the belly down. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The tank pushed through under a shower of dirt and roots, emerging on the far side with its guns still level, its armor still angled, its crew still alive. Bradley turned to the officers beside him. That's it. That's the thing. Get me 500 of those by the 25th. The device that just changed his mind about Operation Cobra had been designed by a 29-year-old sergeant from New Jersey who'd spent the pre-war years as a window dresser for a liquor distributor. Curtis Coolin wasn't an engineer. He had no advanced degree. His formal education ended with Cranford High School, class of 1937, where his greatest achievements were the tennis team and chess club. But Colin understood something the Army's planners hadn't grasped when they studied maps of Normandy back in England. He understood that the bocage, those hedgerows that looked manageable on aerial photographs, were going to kill a lot of tankers. And he understood it because he'd already watched it happen. This is the story of how one sergeant refused to accept impossible, built a SAP prototype from enemy scrap metal, and solved a tactical problem that had paralyzed an army. It's about the distance between seeing a problem and fixing it, and it's about what happens when the guy in the field knows something the generals don't. The bocage country of Normandy wasn't designed for war. It was designed for cows. For centuries, Norman farmers had been piling rocks they found in their fields along property lines, creating boundaries that over time became earthen embankments. The rocks trapped soil, rain carved ditches along the base. Seeds took root in the banks. Blackthorn, oak, ash, and beech grew into tangled masses, roots intertwined underground, binding the earth into something closer to concrete than dirt. By 1944, these hedgerows averaged 4 feet high and ran in irregular patterns across the landscape, carving the countryside into a patchwork of small fields. Most fields were no more than 300 feet across. The hedgerows themselves were sturdy embankments, half earth, half hedge, sometimes reaching 15 feet high at the crest, with root systems so interlocking that excavating them was nearly impossible, even with machinery. For cows and farmers, this system was ideal. For tanks, it was a death trap. When Allied planners studied Normandy before D-Day, they knew about the hedgerows. Aerial reconnaissance had photographed them extensively. Intelligence officers had noted their existence in briefing documents. But nobody, from Eisenhower down to battalion commanders, understood what those photographs meant on the ground. The bocage looked manageable from 5,000 feet. It looked like terrain you could fight through. The first American units pushing inland from Omaha Beach learned otherwise within hours. A Sherman tank approaching a hedgerow had exactly 2 options. Neither good. Option 1 was to try ramming through. The tank would hit the embankment, its nose would start climbing, and momentum would carry it up and over. For a few seconds, the Sherman would sit atop the hedge at a 45-degree angle, its belly exposed, its main gun pointing uselessly at the sky. German soldiers with Panzerfausts, those shoulder-fired anti-tank weapons, could penetrate Sherman belly armor from 200 yards. The crew would hear the explosion, feel the tank lurch, then either burn or bail out if they were lucky. Option 2 was to find a gap. The Norman fields had entrances, spots where farmers had cut through the hedges to move equipment and livestock. But German defenders had spent weeks preparing. Every gap in every hedgerow within miles of the coast was pre-sighted for machine gun and anti-tank fire. A Sherman entering through a gap was entering a kill zone where German gunners had already calculated the range and trajectory. The result was the same: dead tank, dead crew. By late June 1944, American armor losses in the Bocage were approaching catastrophic levels. The First Army had landed thousands of tanks, but effective armor strength was dropping daily, not just from combat losses but from tanks that couldn't maneuver, couldn't support infantry, couldn't do the job they were built for. Infantry units were fighting field to field, hedge to hedge, without the armor support that doctrine said they needed. Coordination between tanks and foot soldiers broke down because the tanks couldn't see beyond the next hedgerow and couldn't move except along predictable routes. German defenders, meanwhile, had adapted brilliantly. They dug foxholes directly into the hedgerow embankments, giving machine gunners overhead protection from artillery while maintaining clear fields of fire across each small field. A German squad with 2 machine guns and a Panzerfaust could hold a position for hours, inflicting dozens of casualties, then fall back to the next hedgerow 200 feet away and do it again. The Allies were advancing at roughly a mile per day in some sectors. At that rate, reaching the open country beyond the Bocage would take months, and months was time the invasion timetable didn't have. Combat engineers tried using explosives to blast holes in the hedgerows. The technique worked, technically. A properly placed charge could blow a gap large enough for a tank, but the explosions attracted immediate German attention. Artillery would bracket the blast site within minutes, and carrying enough explosives to blow a path through miles of hedgerows wasn't logistically feasible. Engineers calculated they'd need more demolitions than the entire army had stockpiled in Normandy. The army tried bulldozer tanks, Shermans fitted with dozer blades on the front. These could push through hedgerows with enough effort, but the modifications were rare. Each division had maybe 4 dozer tanks out of 70 total, and dozer tanks were massive, visible, slow, and became target priority number 1 for every German anti-tank weapon in range. Losing a dozer tank meant losing a capability the division desperately needed. So commanders hoarded them, used them sparingly, and watched the advance stall out anyway. Various units across Normandy tried different solutions through late June and early July. The 79th Infantry Division had a hedge cutter design by early July. The 19th Corps demonstrated a set of prongs initially developed for placing explosives, which could lift portions of hedgerows. The 5th Corps invented devices called brush cutters and green dozers. None of these designs saw widespread use. Some didn't work well enough, some were too complex to manufacture in field conditions. Some required modifications that only depot-level facilities could perform. The fundamental problem remained unsolved. American armor, the weapon system that was supposed to restore mobility to the battlefield, was paralyzed by terrain that looked innocuous on a map, and Operation Cobra, the breakout offensive planned for late July, was going to send the WWII First Army through 40 miles of Bocage country. If the hedgerow problem wasn't solved, Cobra was going to be a disaster. Curtis Grubb Cullen III didn't set out to be an inventor. He set out to stay alive. Cullen was born February 10, 1915, in Cranford, New Jersey, a comfortable suburban town about 20 miles west of New York City. His father worked in the liquor distribution business. His childhood was typical for the era. Depression era, typical, meaning money was tight but the family was stable. He graduated from Cranford High in 1937, played tennis, played chess. No particular distinction beyond being a decent student and a likable guy. After graduation, Cullen's father helped him get a job at Schenley Industries in New York City. Sales promotion assistant was the formal title. Window trimmer was the actual job, computing costs for window displays. General clerking. The kind of position that kept you employed during hard economic times but didn't exactly inspire passion. Cullen stuck with it because jobs were scarce and paying rent mattered. In 1938, he joined the National Guard. The unit was the Essex Troop, a cavalry unit with a proud lineage going back decades. This was still a mounted cavalry troop in 1938. They trained on horseback, held riding exhibitions, considered themselves an elite social organization as much as a military unit. For Kulin, it was weekend warrior stuff, a chance to do something more interesting than window displays, some physical activity, some camaraderie. Then the world changed. By January 1941, the Essex Troop had been federalized, mechanized, and redesignated the 102nd Cavalry Reconnaissance Squadron. The horses were gone, replaced by tanks. Light tanks, M5 Stuarts, which the troopers called sardine cans because the interior dimensions made a phone booth look spacious. Kulin, who'd joined to ride horses, was now training to operate a Calonne, 13-ton armoured vehicle with a 37mm gun. The transformation from Gentleman's Riding Club to Armoured Reconnaissance Squadron was jarring. Cavalry reconnaissance in World War II doctrine meant you were the eyes of the division. You screened ahead of the main force. You found the enemy. You identified their strength. You disengaged before you got chewed up. In practice, especially in Normandy, it meant you were first into every bad tactical situation and last to get support when things went wrong. Kulin shipped to England in October 1943 with the 2nd Armoured Division. Training continued through winter and spring of 1944. By June, he was a sergeant, a tank commander, responsible for a crew and a vehicle in a squadron that was about to land in France as part of the largest amphibious invasion in history. The 102nd Cavalry Reconnaissance Squadron landed on Omaha Beach shortly after D-Day. Not on D-Day itself, the first waves, but in the immediate follow-up, which meant they hit the beach while German artillery was still dropping shells on the landing zones, and the beach was still a chaotic mess of wrecked equipment and casualties being evacuated. They pushed inland immediately. The division's mission was to break out from the beachhead and seize territory rapidly before German reinforcements could establish a solid defensive line. That was the plan. The reality was bocage. Kulin's first experience with the hedgerows came within days of landing. The squadron was probing ahead of the division, trying to find routes through the countryside that wouldn't channel them into German killing zones. What they found was that every route channeled them into German killing zones because the hedgerows created killing zones everywhere. Kulin watched tanks from his squadron try to cross hedgerows and fail. He watched Shermans belly up on the embankments and take Panzerfaust rounds through the thin floor armour. He watched crews bail out, some burning, some just scrambling to get clear before the ammunition cooked off. He watched infantry get pinned down in fields because the tanks that were supposed to be supporting them couldn't advance without exposing themselves. And he started thinking about the problem the way someone thinks about a window display that isn't working, not from an engineering textbook perspective, but from a practical perspective. What's stopping this from working? What's the simplest way to fix it? By mid-July, the 102nd was operating in the Forêt de Cérisy, a wooded area west of Saint-Lô. The tactical situation was grinding, attritional, miserable. Small unit actions, constant German counterattacks, casualties mounting, morale fraying, and everywhere, those hedgerows. Kulin wasn't the only person thinking about the problem. During one of those endless conversations soldiers have when they're waiting for orders or eating cold rations or trying not to think about the last guy who got killed, someone from another unit, a soldier whose name sources identify only as Roberts, a Tennessee hillbilly, according to military historian Max Hastings, made a suggestion. Why don't we get some saw teeth and put them on the front of the tank and cut through these hedges? The reaction, according to accounts, was laughter. The kind of laughter that greets an idea so simple it sounds stupid. Saw teeth on a tank, like you're going to cut through centuries-old root systems and earthen embankments with something you bolt to the glacis plate. Roberts probably got mocked for the suggestion. Somebody probably made a joke about bringing a chainsaw to a tank fight. Kulin didn't laugh. Kulin heard something in the suggestion that other people missed. The principle was sound. Don't go over the hedgerow. Don't try to blast through it. Cut into it. Pin the tank's weight down low and drive through using the engine's power. The idea wasn't stupid. The idea was exactly what, and they needed. It just needed someone to figure out how to make it work. Kulin started sketching, not formal engineering drawings but practical sketches, tank dimensions, hedgerow dimensions, angle of attack. Where would you mount the device? How would you attach it? What would it be made from? He showed his drawings to officers in the squadron, Captain Stephen Lytton, Captain James Depew, who'd recently been promoted, Major Arthur Person. These men weren't engineers either, but they were smart enough to recognize that Cullen had an idea worth testing. The biggest practical question was materials. You needed steel, heavy steel. Angle iron would work, the kind of L-shaped structural steel used in construction. But where were you going to get angle iron in Normandy in July 1944? There were no hardware stores. The supply depots had tank parts and ammunition and rations, not construction materials. Then somebody remembered the beaches. The Germans had scattered obstacles across every landing zone to stop Allied armour from reaching the high ground. Some obstacles were wooden stakes topped with mines, but the most common defensive obstacles were steel, three-beam constructions called Rommel's asparagus. These were welded assemblies of heavy angle iron designed to rip the belly out of landing craft or impale tanks trying to cross the beach. The Allies had destroyed or bypassed thousands of them during the landings. Many were still sitting on the beaches, scrap metal nobody had bothered to collect. Cullen realized he was looking at his raw material, German steel, heavy gauge, already cut into manageable lengths, free for the taking. By late July, Cullen had a prototype, 4 prongs, welded to a crossbar, attached to the front of his light tank. The prongs were angled slightly downward, designed to bite into the base of a hedgerow embankment rather than ride up over it. The whole assembly weighed maybe 300 pounds, not enough to affect the tank's mobility significantly, but sturdy enough to withstand the force of driving through dirt and roots. The test was informal. Cullen's tank, a hedgerow in a quiet sector. The crew backed up, accelerated, and hit the embankment at 10 miles per hour. The prongs dug in, the nose stayed down. The tank pushed through, tearing a gap wide enough for infantry to follow. It worked. Not perfectly. Some dirt fell into the driver's vision slit. The hedgerow didn't disintegrate. It tore open, leaving debris that other vehicles would have to navigate around. But compared to bellying up and exposing the underside, compared to looking for gaps that were pre-sighted kill zones, compared to waiting for engineers to blow holes with explosives they didn't have enough of, this was a miracle. Word spread fast through the division. A sergeant in the 102nd had figured out the hedgerow problem. Officers came to watch demonstrations, then higher-ranking officers, then General Guerreau, commanding the 5th Corps, called General Bradley and said, "You need to see this." On July 14th, 1944, Bradley arrived at a field near Isigny, where Cullen's device had been fitted to both a light tank and a Sherman. Bradley watched the demonstration. Both tanks charged hedgerows and broke through without exposing their belly armour. So absurdly simple, Bradley would later write in his memoir that it had baffled an army for more than 5 weeks. Bradley understood immediately what he was looking at. Operation Cobra, the breakout offensive scheduled for July 25th, was going to send the First Army through exactly the kind of terrain where hedgerows had been killing tanks for 6 weeks. If American armour could break through hedgerows without vulnerability, Cobra had a chance. If armour remained paralysed by the bocage, Cobra was going to be another grinding attritional nightmare. He turned to Lieutenant Colonel John Medaris, the First Army's ordnance officer, and gave an order that would change the campaign. "I want every ordnance unit in the Army on round-the-clock production of these devices. Scrap metal for the tank tusks would come from Rommel's underwater obstacles on the beaches. Get me 500 of these by July 25th. Medaris didn't hesitate. He sped back to First Army headquarters and issued orders, putting every maintenance company, every repair depot, every unit with welding equipment to work, fabricating hedge cutters. By evening, they'd discovered they didn't have enough arc welding equipment to support the production rate Bradley wanted. Medaris jumped on a plane to England at 6 that evening and conscripted the supply depots there. A plane flew welding equipment back to France overnight. Trucks were waiting at the airstrip when it landed before breakfast. Within a week, 3 out of every 5 tanks in the First Army breakout force had been equipped with what was now officially called the rhinoceros device, though everyone just called them rhinos. The name came from the tusks, the way the tank charged through obstacles like an African rhinoceros. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Culin's invention became the Cullen hedgerow cutter. His name became attached to a device that was being manufactured by the hundreds while he was still a sergeant in a reconnaissance squadron, wondering if he was going to survive the war. For his invention, Culin received the Legion of Merit, a decoration typically reserved for officers who demonstrated exceptional service. Eisenhower mentioned him in speeches. Bradley wrote about him in his memoir. Culin became, as Max Hastings put it, a very American kind of national hero, the honest man who saw a problem, built a solution, and changed the war. But the story doesn't end with the award ceremony or the headlines. The war kept going, and Curtis Cullen kept serving. 4 months after his invention changed the Normandy campaign, Cullen was fighting in the Hurtgen forest near the German-Belgian border. On November 2nd, 1944, he was walking at night with another soldier from Cranford, William Bateman. Cullen stepped on an anti-personnel mine. His left leg was shattered. As he fell, he detonated a second mine, which severely wounded his right thigh. He survived, lost the left leg, spent months in hospitals, returned home to New Jersey in 1945, 29 years old, decorated war hero, missing a limb, facing the prospect of rebuilding a civilian life. He married Bernice Enright in 1945, went back to work for Schenley Industries as a salesman, moved to New York City, lived quietly. By all accounts, he didn't talk much about the war or the invention. He was the guy who'd figured out the hedgerow problem, but in day-to-day life he was just Curtis Cullen, liquor salesman, trying to pay rent and build a normal existence. He died November 20th, 1963, in Greenwich Village, Manhattan, 48 years old. Heart attack, most likely, though sources don't specify. No dramatic ending. No battlefield heroics at the end of his story. Just a man who'd done something extraordinary during a war and then lived the rest of his life as an ordinary person. His obituary in the Cranford newspaper noted his military service, but said nothing remarkable about the invention that had made him famous 20 years earlier. The rhinoceros device, meanwhile, had become part of the permanent record. The solution that restored mobility to American armor during the breakout from Normandy. The innovation that helped make Operation Cobra possible. By the time Cobra launched on July 25, 1944, approximately 60% of First Army tanks were equipped with Cullen's modification. Shermans, Stuarts, even some M10 tank destroyers. The Germans had no idea these modifications existed. The Allies had kept the rhinos hidden, not using them in combat until Cobra kicked off. When American armor smashed through the hedgerows on the Taimens, the first day of Cobra, without exposing their belly armor, German defenders were caught completely off guard. The defensive positions they'd prepared, the kill zones they'd established, the tactics they'd developed specifically to exploit the hedgerow terrain, all became substantially less effective. American tanks could now push through embankments, support infantry in real time, and maintain momentum through terrain that should have stopped them cold. The breakout from Normandy succeeded for many reasons: air support, artillery, infantry courage, German mistakes. But one of those reasons, buried in the operational reports and casualty statistics, was a device invented by a sergeant who'd been trying to keep his crew alive and had refused to accept that the problem was unsolvable. The lesson isn't really about hedgerows or tanks or Normandy. The lesson is about the distance between someone telling you something can't be done and you doing it anyway. The Army's planners hadn't solved the hedgerow problem because they'd been looking at it from 20,000 feet, literally. Aerial photos and maps and intelligence summaries, all useful, none sufficient. Curtis Cullen solved it because he was looking at it from ground level, from inside a tank, with a very personal understanding of what happened when you tried to cross a hedgerow the wrong way. He solved it because he wasn't constrained by formal engineering training that might have told him all the reasons his idea wouldn't work. He solved it because he was practical rather than theoretical, and he solved it because he had access to scrap metal that nobody else had thought to repurpose. The Germans had given the Allies the raw materials for their own defeat. Those beach obstacles, designed to stop the invasion, ended up as the primary component in a device that helped win the campaign beyond the beaches. There's a certain irony in that, the kind of irony that only becomes visible in hindsight. The British Royal Electrical and Mechanical Engineers, watching American tanks plough through Norman hedgerows in late July, immediately recognized they had the same problem. British armour in the eastern sector around Caen was facing identical bocage terrain. The difference was that the British had been too focused on breaking through German panzer divisions to notice that the landscape itself was killing their mobility. Within days of seeing the American rhinos in action, British Reme units began fabricating their own versions, which they called prongs. The design was essentially identical to Cullen's, 4 steel tusks welded to a mounting plate, attached to the glacis of a Sherman or Cromwell tank. But the British, being British, systematized the production in ways the Americans hadn't bothered with. They designated 3 different marks of prongs: Mark I for Sherman 5s, Mark II for Shermans and M10 tank destroyers, Mark III for Cromwell tanks. By August 1944, British factories were producing prongs at scale. 600 Mark I's delivered in August, another 1,000 Mark IIs, 500 Mark IIIs. Even Churchill tanks, which theoretically didn't need hedge-breaching devices because of their superior ground clearance and climbing ability, got fitted with prongs. Better to have the capability and not need it than need it, and watch your tank belly up into a Panzerfaust. The Canadians adopted the design immediately. Canadian armoured units fighting their way south from Juno Beach faced the same hedgerow nightmare the Americans had encountered. Canadian ordnance companies began manufacturing their own versions, using steel, scavenged from German beach defences and damaged vehicles. No formal designation, no bureaucratic approval process, just welders working overtime to equip tanks before the next push. What's remarkable about the spread of the rhinoceros device wasn't the technology transfer, it was the speed. In most military procurement systems, adopting a new piece of equipment takes months or years. Requirements, documents, testing protocols, contracts, supply chain establishment. The Rhino bypassed all of that because it wasn't being adopted through official channels. It was spreading through word of mouth and direct observation. Tank crews saw it work. Officers saw it work. Maintenance personnel figured out how to build it, and everyone just started doing it without waiting for permission. This was field innovation in its purest form. Soldiers identifying a problem, seeing a solution, and implementing it immediately, using whatever materials were available. The fact that High Command eventually blessed the modification with official approval was almost beside the point. By the time the paperwork caught up, thousands of tanks were already running Rhino devices welded on by company armourers who'd learned the technique from watching someone else do it. The impact on Operation Cobra was substantial but difficult to quantify precisely. Cobra succeeded for multiple reasons, some of them having nothing to do with hedgerow cutters. The weather cleared after days of delays, allowing massive aerial bombardment. German defensive positions had been worn down by weeks of attritional combat. American infantry had learned, through bloody experience, how to fight in bocage terrain. Artillery had refined techniques for supporting small unit actions in enclosed spaces, but every after-action report from armoured units involved in Cobra mentions the Rhino devices as a critical factor in maintaining momentum. Tanks could advance without waiting for engineers to blow gaps with explosives. They could support infantry in real time rather than being channeled into predictable routes. They could maneuver through terrain that should have been impassable, which meant German defenders couldn't predict where American armour would appear. The psychological impact on German forces was significant. The bocage had been their ally for 6 weeks. Every hedgerow was a potential defensive position. Every narrow lane was a kill zone. They'd watched American tanks try to cross hedgerows and fail repeatedly, exposing themselves to Panzerfaust fire. German anti-tank crews had developed tactics specifically around that vulnerability. Then suddenly, in late July, American tanks started smashing through hedgerows at ground level, nose down, guns forward, belly armour protected. The defensive calculations that had worked for weeks stopped working. German unit reports from late July and August 1944 reference the American tank modifications with a mixture of surprise and frustration. They hadn't anticipated this adaptation. Their intelligence hadn't warned them, and they didn't have an immediate counter. You can't ambush a tank that doesn't have to use the roads you've mined. You can't position Panzerfaust teams to hit belly armor when the belly armor stays horizontal. The operational tempo of Cobra reflected this shift. In the first 3 days of the offensive, July 25th through 27th, American forces advanced further than they had in the previous 6 weeks combined. Armor that should have been slowed to a crawl by bocage terrain was maintaining speeds of several miles per hour, which doesn't sound fast until you remember that before Cobra, gains were being measured in hundreds of yards per day. By early August, the breakout had succeeded. American armor was in the open country south of the bocage, racing toward Brittany and the Loire Valley. The campaign entered a mobile phase where tanks could finally do what they were designed for: exploit breakthroughs and encircle enemy forces. The Falaise Pocket, where Allied forces trapped and destroyed much of the German 7th Army in mid-August, was possible because armor could move rapidly through terrain that should have slowed them. Curtis Culin never claimed credit for winning the Normandy campaign. He was too practical for that. In the few interviews he gave after the war, he emphasized that his device was a small piece of a much larger effort. Thousands of soldiers were solving problems every day. His solution just happened to be visible and scalable. But the generals who commanded the campaign understood what Culin's invention had enabled. Eisenhower mentioned him by name in a 1961 speech to the American Society of Mechanical Engineers, calling him a little sergeant with an idea that changed warfare in Normandy. Bradley devoted several paragraphs to Cullen in his memoir, describing the demonstration he'd witnessed and the scramble to equip the First Army before Cobra launched. Bradley understood that warfare wasn't just about grand strategy and operational planning. It was also about logistics, maintenance, and the occasional sergeant who saw a problem nobody else had solved and fixed it with scrap metal and a welder. The broader lesson about military innovation is worth examining because it contradicts how most people think innovation happens. The standard narrative says innovation comes from research labs, from scientists with advanced degrees, from formal programs with budgets and timelines. Sometimes that's true. Radar came from research labs. The atomic bomb came from the Manhattan Project. Penicillin came from systematic scientific investigation. But a surprising amount of military innovation in World War II came from people like Culin, enlisted personnel or junior officers who were close enough to the problem to understand it viscerally and practical enough to improvise solutions without waiting for official guidance. The rhinoceros device didn't emerge from a Pentagon study group or an engineering department at General Motors. It emerged from a sergeant looking at a hedgerow and thinking there has to be a better way. This pattern repeated throughout the war. The best anti-submarine tactics in the Atlantic weren't developed by naval theorists at staff colleges. They were developed by commanders like Frederick Walker, who spent months hunting U-boats and refined their techniques through trial and error. The most effective close air support tactics in the Pacific weren't codified in doctrine manuals. They were invented by pilots and ground controllers who learned through experience what worked and what got people killed. The challenge for military organizations is creating an environment where this kind of bottom-up innovation can happen. Large hierarchical institutions are naturally resistant to change, especially change that comes from below. There are good reasons for this. Standardization matters. Logistics matters. You can't have every unit inventing their own solutions because then you can't supply them or replace their equipment when it breaks. But taken too far, that resistance to change becomes paralysis. You end up with an army that can't adapt faster than the enemy adapts. The American army in World War II was better at this than most militaries. Not perfect, but better. Officers like Bradley and Eisenhower understood that good ideas could come from anywhere, and that speed of implementation mattered more than bureaucratic perfection. When Cullen demonstrated his device, Bradley didn't convene a committee to study it. He didn't send it back to the United States for engineering evaluation. He watched it work, understood its value, and ordered immediate mass production using field resources. That kind of decision-making requires trust in subordinates and tolerance for improvisation. It requires accepting that field-expedient solutions won't be perfect but might be good enough. The Rhino devices weren't elegantly engineered. Each one was slightly different because they were hand-fabricated by welders working from rough specifications. Some were heavier than necessary, some were lighter than ideal. Quality varied depending on who did the welding and what steel they used. None of that mattered because they worked well enough to restore tactical mobility to American armor, and working well enough in July 1944 was infinitely better than waiting for a perfect solution that might arrive in September. The German army, by contrast, struggled with this kind of adaptation. They had brilliant engineers and sophisticated weapons development programs, but their institutional culture made field improvisation difficult. Modifications had to go through approval channels. Changes to standard equipment required authorization from higher command. This meant German units could identify problems quickly, but couldn't solve them quickly. By the time a solution made it through the approval process and into production, the tactical situation had often changed. There's a specific example from Normandy that illustrates this. German panzer crews figured out early that Sherman tanks had thin side armor and that hitting them from the flank with the 75mm gun on a Panther or Tiger was almost guaranteed to destroy the target. This was valuable tactical knowledge. But German commanders didn't systematically train their crews on this technique or develop doctrine around it. They just expected experienced crews to figure it out. Meanwhile, American tank crews were learning through after-action briefings and formal instruction that German armor was vulnerable in specific spots, and here's how you identify those spots, and here's the angle you need to hit them from. The result was that American tactical adaptation happened faster than German tactical adaptation, even though German equipment was often superior at the individual vehicle level. Better training systems, better communication of lessons learned, better tolerance for field-expedient solutions. These advantages compounded over time. An army that can adapt 10% faster than its opponent gains cumulative advantage with every engagement. Curtis Culin's invention was one data point in that larger pattern. It wasn't the thing that won the war, but it was representative of the kind of practical problem-solving that American forces did consistently well. See a problem, try a solution. If it works, scale it. If it doesn't work, try something else. No wasted time debating theoretical perfection, no paralysis from overthinking. Just bias toward action and willingness to accept that good enough today beats perfect tomorrow. The human cost calculations are harder to pin down precisely, but they matter. Every tank that crossed a hedgerow with a Rhino device instead of bellying up was a tank that didn't expose its crew to Panzerfaust fire. Every crew that survived because their tank stayed horizontal through a breach was a crew that could fight the next engagement. Multiply that across hundreds of tanks over weeks of combat, and you're looking at possibly thousands of casualties prevented. The numbers aren't in the historical record because nobody tracked casualties prevented, only casualties incurred. But tankers who served in Normandy after the Rhino devices were deployed understood the difference. They'd watched crews die when tanks bellied up on hedgerows in June and early July. They'd watched the same maneuver work safely once Rhinos were installed. The calculus was simple and brutal. Before Rhinos, crossing a hedgerow was a coin flip on whether you'd survive. After Rhinos, crossing a hedgerow was dangerous but manageable. That difference kept people alive. There's also the question of morale, which is difficult to quantify but crucial for combat effectiveness. An army that believes its equipment is inadequate for the mission it's being asked to perform is an army with deteriorating morale. American tankers in June 1944 were watching their vehicles fail in ways that got people killed. The Sherman was already controversial, undergunned and under-armoured compared to German heavies. Now it couldn't even handle terrain. That's corrosive. That's the kind of thing that makes soldiers question whether their leadership knows what it's doing. The Rhino devices helped reverse that spiral. They demonstrated that command was listening to problems from the field and responding with practical solutions. They proved that American maintenance and logistics capabilities could adapt quickly to battlefield needs. They gave tankers a tool that worked, which restored confidence that the institution could solve problems when those problems became critical. Good morale doesn't win battles by itself, but bad morale loses battles that should have been winnable. Eisenhower understood this when he mentioned Kulin in his speeches years after the war. He wasn't just praising one sergeant's cleverness, he was highlighting a moment when the institutional army had worked the way it was supposed to work. Problem identified at ground level. Solution developed at ground level. Support provided from higher command to scale that solution across the force, and all of it happening fast enough to matter for the current operation rather than the next operation. The story ends, as most war stories do, with the return to normal life. Cullen came home, married, worked as a salesman, lived in New York. By all accounts, he didn't trade on his fame. He didn't write a memoir or give lecture tours or position himself as a military consultant. He just went back to being a civilian, dealing with the physical and psychological aftermath of combat like millions of other veterans. His legacy wasn't the celebrity or the awards. His legacy was the maintenance facility at Fort Knox that was named after him, the Cullen Field Maintenance Shop, where soldiers learned how to keep armoured vehicles operational. His legacy was the footnotes in history books about the Normandy campaign that mention the rhinoceros device as a critical tactical innovation. His legacy was every tank commander who crossed a hedgerow safely because someone had welded steel tusks to the front of their Sherman. The plaque, dedicated to Cullen in Cranford, New Jersey, mounted on a boulder on the North Union Avenue side of the municipal building, summarizes his contribution in a few sentences. Native son who helped break through the bocage, served with distinction, wounded in combat, came home. That's the story reduced to its essentials. What it doesn't capture is the moment when one person's refusal to accept impossible changed the trajectory of a military campaign. The Rhino device became obsolete within months. Once Allied forces broke out of Normandy and entered open country, hedgerow breaching equipment wasn't necessary. Tank crews removed the tusks to reduce weight and improve maneuverability on roads. By the time American armor reached the German border in September 1944, most Rhino devices had been discarded or recycled. They'd served their purpose. The problem they solved no longer existed. That's typical for field expedient solutions. They're designed for specific problems in specific contexts. When the context changes, the solution becomes unnecessary. But the thinking behind the solution, the willingness to improvise and adapt, that remains valuable regardless of context. The armies that win wars aren't necessarily the ones with the best equipment or the most soldiers. They're the armies that can solve problems faster than problems emerge. They're the armies that empower people at every level to see what's broken and fix it. Curtis Cullen saw what was broken. He fixed it. The fix saved lives, changed a campaign, and became a case study in how military innovation actually happens when you strip away the mythology. No eureka moment, no lone genius working in isolation, just practical problem-solving, institutional support when it mattered, and the courage to propose a solution that looked too simple to work. The hedgerows of Normandy are still there. The fields still have those earthen embankments, though they're lower now and less tangled than they were in 1944. Farmers have modernized. Tractors have made the old field boundaries less necessary. But you can still walk the bocage country and see the terrain that stalled an army for 6 weeks. If you know where to look, you can still find rusted pieces of German beach obstacles in the sand, the same obstacles that became the raw material for thousands of Rhino devices. The steel that was supposed to stop the invasion ended up helping to win it. That irony would probably have amused Cullen, who understood that wars are won with whatever materials you can scrounge and whatever ideas actually work rather than the ideas that should work according to theory. The broader lesson extends beyond World War II, beyond Normandy, beyond tanks and hedgerows. It's a lesson about the distance between doctrine and reality, between what's supposed to happen and what actually happens when plans collide with circumstances. Military organizations spend enormous resources developing doctrine, training personnel, acquiring equipment, all necessary, all important. But doctrine can't anticipate every situation. Training can't prepare soldiers for every contingency. Equipment won't be perfect for every mission. The armies that succeed are the ones that accept this reality and build institutions capable of rapid adaptation. They're the armies that listen when sergeants say the equipment isn't working and here's how to fix it. They're the armies that empower field-grade officers to authorize modifications without waiting for approval from the Pentagon or the War Department. They're the armies that understand perfection is the enemy of good enough, and that good enough deployed in July beats perfect arriving in September. Curtis Coolin embodied that approach. Window dresser turned tanker turned inventor turned casualty turned survivor turned anonymous civilian. His contribution to the war was disproportionate to his rank or his training or any reasonable expectation based on his background. But that's how innovation often works. The person who solves the problem isn't the person you'd predict would solve it. They're just the person who was paying attention, who refused to accept that the problem was unsolvable, and who had access to a welder and some scrap metal. The rhinoceros device wasn't elegant. It wasn't sophisticated. It probably wouldn't have passed engineering review if it had been submitted through formal channels. But it worked, and in July 1944, in the hedgerows of Normandy, working was all that mattered. Thousands of tank crews who crossed those hedgerows safely owed their survival to a sergeant from New Jersey who'd figured out how to keep the nose down and the guns forward. That's worth remembering, not just as military history, but as a reminder that complex problems sometimes have simple solutions, and the person who finds those solutions might be anyone willing to look at the problem from a different angle. Curtis Coolin looked at hedgerows from inside a tank and saw a problem that could be solved with steel and welding. The army listened. The solution scaled. The campaign succeeded. And one sergeant's crazy device turned Sherman tanks into unstoppable rhinos that helped liberate Europe. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.